Cyanide can kill you, okay? Now, by the way, our bodies produce hydrogen cyanide every day. Every one of you right now are producing hydrogen cyanide as part of your normal metabolic process. Ignore that for a moment. I've got a jar of hydrogen cyanide, okay? Now then, that's the hazard. Now I take that jar and I put it into a locked metal vault, okay? And I seal it in that metal vault. What have I done to the hazard? I've isolated, I've contained it. Have I changed it? No, I didn't change it. The only thing I changed was the risk that that hazard is going to be realized. Now, I take that locked vault and I give it to my boss, and she takes it back to our offices in Park County. What have I done to the hazard? Nothing. I've changed the risk. If it's in Park County, nobody here is going to be exposed to it, therefore there can be no risk. Now I take that jar of hydrogen cyanide, though, and I put it right there and I balance it on the edge of that table. I have not changed the hazard. It's still the same hazardous situation. I have changed the risk. By balancing it on that table, I have now made it more probable that the hazard will be realized, somebody will be exposed. So once I take that jar of hydrogen cyanide, I put it in the vault, I give it to Chris, she takes it back to her office. What I've done is I've attained an acceptable level of risk, which is safety. Safety is a funny thing because it is irrational. Every one of us, when we got up this morning, we have a 1 in 10 million chance of not making it to bed. That is your background risk from all causes. Car accidents, cancer, stroke, murder, old age, whatever it happens to be, our cumulative risk of not making it back to bed every day is 1 in 10 million. We have a 1 in 10 million risk. Almost all of you drove here. Driving is going to be the highest risk thing that you probably do every single day. It's dangerous, okay? And yet, you don't have a problem doing it. You don't have a problem doing it because you think it's safe. And you think it's safe because you're comfortable with the risks. You think you understand the risks. And so there's a certain irrational aspect to safety that tells us that something is acceptable to assume those risks, okay? Swimming, I don't swim, I'm a sinker. I hit the water, I go straight down. Okay, so for me, water is just scary stuff. I'm an idiot when it comes to things like electricity. So you don't want me anywhere near wiring because something's going to blow up. It's risky. But as we become more familiar with certain things, now, okay, I'll go into a meth lab because I understand it. I understand what's going on. As some of you know, I'm a cop. I have absolutely no problems going into an active shooter situation. I've been involved in several because I understand those risks. I can control them. So there's an irrational side to safety. But empirically, safety is the attainment of an acceptable level of risk. So who determines that acceptability? Now that's a trickier issue. That's a very different issue. Hazard is the totality of all epidemiological, toxicological, and biological knowledge without regard to probability. Something is hazardous, and that's it. It is hazardous without regard to probability. The source, it'll be the source of a risk. If you remove the source, you cannot have a risk. As long as there's a source, there's always risk. Risks can be positive or negative. So let's go back again to the water situation. I need a certain amount of water. If I don't have water, homeostasis goes awry and I become ill. Okay, that's a negative risk. But then I start to consume a certain amount of water and now my risk goes down. So it's a negative correlation until I drink too much and then the risk starts going back up again. Okay, so risks can be negative or they can be positive. Positive risks indicate a deleterious effect, an adverse effect. Negative risks indicate the avoidance of a deleterious effect or a beneficial effect, sometimes referred to as hormesis. So you can have positive or negative risks. We all behave differently to the same exposure. If right now we're sitting here, there's something goes wrong with the ventilation system, and say 8 parts per million of carbon monoxide starts to enter into this room, and we got, well, I don't know, 30 people here. Comes into the room, some of you at 8 parts per million would get a headache. 1 or 2 of you might even start to throw up. Most of you would not even notice anything. And then, as I increase the carbon monoxide inside here, now more and more people are getting headaches. More people are starting to throw up. But there's still going to be a couple of you that are going, oh, what's going on? Because you're not feeling the effects. So as a population, we respond differently to the same dose because we are different. So I'm going to take my bottle of whiskey, I'm going to take my fish, and I'm going to be an amateur toxicologist. I'm going to start to see what effect does whiskey have on fish. So I've got my tank of fish, and I take my bottle of whiskey, and I take an eyedropper, and I start putting it in drop by drop by drop, and I observe the fish. And nothing happens. So, oh, heck with this. So I take a shot glass, and I dump a glass of whiskey in there. Nothing happens. 2 glasses, nothing happens. 3 glasses, nothing happens. I've established what's known at this point as a NOEL, a no observable adverse effect level, a NOEL, no observable effect level. I've established that with my fish tank of that size, I can throw in 3 shots and I don't have a problem. Now I get up to 5 shots and suddenly I've got a fish swimming upside down. Okay, I've just established, now I've established another toxicological set point called the LOEL, the lowest observable adverse effect level. So I know that if I put in 3, I don't have an effect. If I put in 5 shots, I kill at least 1 fish. Well, there's an uncertainty. Now what would happen at 4? Well, I don't know yet. I don't know. So there's an uncertainty point in there. But I have established a NOEL and a LOEL. And that's why right now as we sit here and we breathe carbon monoxide, we're probably around 0.5 to 2 parts per million of carbon monoxide in this room right now, we are all below the toxicologically significant concentration. That is, we are all below the NOEL. And so although carbon monoxide is a hazardous material and we are all exposed to it, we're all breathing it in, none of us are having any deleterious effects to it because it's below the NOEL, the toxicological NOEL. Now I continue to increase it. Now I put in 10 shots of whiskey and now I have half the fish dead. I've established what's known as the lethal dose 50%, the LD50, or the effective dose 50%. And now I continue to increase it. I throw in 15 shots and all of the fish are dead, but the Irish fish, this is the Irish fish down here. The Irish fish is still alive because we've got rock solid livers. We just metabolize that stuff, no problem, right? So we've got Irish fish down here. He is the one who is the resilient in that population. At 5 shots, we had somebody who was sensitive. At 15 shots, we've got somebody who's resilient. So at any given dose, we're going to have a specific response. And what we've established now is called a dose-response relationship. This is an important part of toxicology and predicting risks. Is we look at doses and responses, and we look at the relationship between the one as it impacts the other. This is known as a dose-response relationship, and in the case of our whiskey and our fish, we have established what is called, and you can see, you look at this graph, and graphically you can kind of see where I'm going with it, is we have a linear dose-response relationship. So we've established in our little experiment here, we've established that as we increase the shots of whiskey, those are our units, shots, that we have a proportional deleterious effect. That means that we can now predict it. We can, with some degree of confidence, we can predict if we have 10 million fish and the tank is proportionally larger, how much more whiskey do we have to pump in there before we get an observed effect. So it allows us to make predictions. So we've established what's called a linear dose-response relationship. Again, we all behave differently though, so when we're doing these risk estimates, we have to remember we have both sensitive individuals and we've got resilient individuals. So as toxicologists, typically what we do is we focus on the sensitive individuals. Sometimes we're wrong. For example, those who are here for my meth talk, I was the guy that did the review on the toxicological body burden for the state of Colorado on the meth standard. And we used what we thought was going to be the most sensitive model, which was an infant paddling around on the ground, picking up things, putting things into her mouth, and down into the dirty and the nasty of a meth lab. And so we used an infant. Our second most sensitive model was a pregnant woman, and our least sensitive model was what's called model man, 23-year-old white male in good health. All right? Well, we were wrong. Turns out model man is the most sensitive model. That was actually the sensitive person. The baby was much less sensitive than model man, and the pregnant woman even less so again. So we're not always correct in our assumptions, but that's the study of epidemiology, which is the occurrence of endpoints. So we look at presence, then we look at exposure, and then we calculate risk. So to do that, then we have to introduce some new words. These words are very important because now we're going to get into what I'm going to call the disingenuosity of some of the literature. The EPA says, radon is associated with lung cancer. Radon is correlated with lung cancer. Well, why doesn't the EPA just come out and say radon causes lung cancer? Why don't they just say cause? Why are they using the word associate? Why are they using the word correlate in their little pamphlets? It seems a little bit ambiguous. Association. Association is an epidemiological term, and it simply means that one event occurs in relationship to another event without any further quantification. Association is the lowest level of evidence in epidemiology. It is the weakest possible link. And we're going to go into some of the language the EPA uses here. But essentially, association is a meaningless term. I could easily say that blue shirts are associated with lung cancer. And that would be an accurate statement. Because I haven't quantified it. I have not given any empirical quantification to it whatsoever. This is a real example. I got a phone call, and a woman called me up, and she wanted me to come and test a house for her that they had bought. I said, what do you want me to test the house for? She said, my house is killing people. Okay, explain to me why you think the house is killing people. Here's what she said, and this is all rational, very rational. She said, the last person who lived in this house died of lung cancer. That's an objective statement. That's an objective fact. Then she said, the last 5 occupants of this house have also died. Again, that is an objective observation. That's not an opinion. It's not subjective. She can take you to the grave sites and she can show you on the deed who lived there, and they are now dead. So that's an objective statement of fact. Therefore, the fact is occupancy in the house is associated with death. That's an objective statement. Then she jumped into a logical fallacy. She concluded the house is causing people to die. So we've gone from association to causation. And we never even covered the ground in between. And so her assessment that the house was causing people to die was countered when I pointed out the 2 following points that were missing from her argument, which is this. Virtually all people who have died have lived in a house. And absolutely all people who have lived in a house will die. Those 2 are also objective facts. And so this made her think, and I said, listen, what if you've got a house built in the 1850s? And now you go and you track down all the people that lived in that house. How many of them do you think are still alive? Okay, and then ask the follow-up question is, how many of those who are surviving will ultimately die? Well, from that, then you can conclude that that house is absolutely associated with death because 100% of the people who have occupied the house are either dead or will die. But that doesn't mean the house is causing any of the deaths. It merely means that it's associated. So all houses are associated with death. So what's missing? What's missing is correlation. A correlation is a quantification of association. It's adding something else empirically to tie in an association with the occurrence that's observed. So it's an empirical assessment of association. It is a type of a quantified association. It's stronger than an association. It's required to demonstrate causation, but it's independent of causation. Correlation is not causation. Neither is correlation association, nor is association causation. It's an event that is observed to change with another event, and it can be positive or negative. Go back to my fish. We had a dose-response relationship. We knew there was an association between the number of shots that were put in and fish dying, and then we quantified it by increasing the amount of whiskey that we were putting in there until we saw that there was actually a proportionality between the two. We had a causative agent and we had an effect. Now, by the way, we don't even know what's in the whiskey that's killing the fish. We assume it's alcohol, but we don't know that. We just have made that assumption. That's probably a pretty good assumption. It's 50% alcohol. Occam's razor says, well, the most obvious is probably the best guess. So we'll go ahead and we'll make that assumption. But it can be positive or it can be negative, a correlation. So, do storks cause babies? Is the question even intelligent? Do storks cause babies? Believe it or not, somebody actually studied the question. And we look at this because it is important. A genuine, 100% scientific study showed that in Oldenburg, Germany, when they looked at the stork populations between 1930 and 1936, what they found was that there was a positive correlation between stork populations and live birth of babies. And that association, the correlation associated with the association, was almost perfect. It had a linear regression of 0.95. A linear regression of 1 is a perfect association. It's a perfect correlation, it's a perfect correlation. They found almost near perfect correlation between stork populations and humans, human live birth. So can we conclude, well, gosh, we've got great correlation, we've got association. Do storks cause babies? How about this? Do lynx cause sunspots? Somebody actually studied it. And they went and they looked at the population of Canadian lynx and solar spot activity. And what they found was, not only is there a positive correlation, there is a negative correlation, and there is a spatial correlation and a temporal correlation. They found almost near perfect correlation between Canadian lynx populations and solar activity. So now we go, well, wait a minute, you got association, you got correlation, surely that causes causation. These two examples show that there's still something missing. Just because somebody has good association, somebody can statistically show great correlation, there's something else missing, and that's called common sense. Because we know that Canadian lynx don't cause sunspots, or vice versa. So there's what's called a confounder in there somewhere. And we just don't know what the confounder is. Okay, well actually we do, but if you want to come to one of my toxicology lectures, I'll tell you why. But it's called a confounder. So without knowing what these confounders are, it's very easy for somebody who's agenda-driven to say, oh, I have done a study and I have shown great correlation between X and therefore it's correlated with Y and it's almost perfect correlation, therefore X causes Y. But it's a fallacy. Or it may be a fallacy, without more information, without asking more questions. So when we look at correlation, we look at numbers. I often talk about playing the numbers game. People, who remembers the book, How to Lie with Statistics? It's a great little book. You can read it in an hour and a half. How to Lie with Statistics. And you read that and you'll understand when people are talking about some of the numbers, especially percentages, where these things come from. And how you can distort the presentation of data by just selecting your words very carefully, and you'll speak 100% truth. I'm Catholic, we call it a broad mental reservation. Okay, it's a philosophical idea of I say something to you, and I know how you're going to take it, And although I've said it correctly and accurately, I know that how you've received it is not accurate. But I've done it anyway. Broad mental reservation. The ability to say something that presents information in a certain way that I know my recipient is going to receive it in a way other than what is actually accurate. Broad mental reservation. And this game is played with correlation all the time. Let's take a look at this. This is a good example of correlation. We have a linear correlation between one event and another. Graphically, we look at it and we go, intuitively, this makes sense. As one event occurs and increases, so too increases another event. I look at that and I go, that's good correlation. It's 0.85. That's great correlation. Statistically, surely that must demonstrate that one thing is occurring dependent on another thing. But here's the numbers game. Each of these graphs all show a correlation of 0.85. So although intuitively we can look at that and go, well, 0.85, that's really clear. As one thing happens, another thing happens. But what about this? That's also 0.85. And as we can see, we have a variable, a dependent variable and an independent variable, and the dependent variable is not dependent on the independent variable. It's completely disassociated. But numerically, it is still 0.85. Here we have something very close to the radon risk curve. We have something that appears to increase with increasing concentrations, but if we continue this and we use that model, we're going to see that now the effect goes down as the other event goes up. And yet it's still the same correlation. Here's what we saw with regard to the lynx and with regard to the storks and the babies. We see a scatter plot that is trending. The one trends with the other. The effect is trending with the what's called the insult, the thing that's driving the train. So for causation, there must be a plausible biological response. Now we can eliminate storks and babies and Canadian lynx and sunspots because we have no plausible biological response between the two. We can just say common sense tells us that's not there. There must be a strong and consistent correlation, and when the event is removed, it must result in an effect that also fails to appear. This has never been done with radon, ever, in any epidemiological study. Why do you suppose that is? It's because we're all breathing radon anyway, every day, every one of us. It is physically impossible to remove a human from a radon atmosphere. So, we go back to our lowest observable adverse effect level. It is the lowest exposure level at which there are statistically significant increases in frequency or severity of adverse effects. It's usually going to be derived from animal studies, not always. In the case of radon, it isn't. And even human studies may have some animal modifications. So here's what the risk curve looks like for virtually any non-radiological and some radiological insults. So we have, with regard to response, an increasing dose. We have error. These are error bars. It tells us where our error is. We have a NOEL. Below that, we don't see an effect. We have a LOEL. This is where we have some issues. These may be beneficial. They may be deleterious. We don't know. But then we reach a point where now above the lowest observable adverse effect level, now we have an increase in response. This is known as a sigmoid curve, and between these 2 points, it's a linear relationship. This is very common to see this linear relationship right here. We're going to come to back to this in a second. The graph also shows us a couple of other things. It shows us that this is asymptotic, meaning if we stretch this thing out, this never gets to 0. And as we stretch this thing out, this never gets to 100% response. We'll always have a resilient population, and we'll have a sensitive population. So, now we say, okay, what about radon? How does this all tie in with radon? Well, when we look at the dose risks curves of radon, and as scientists, not EPA, As scientists, when we look at the actual epidemiological evidence, we have to take where we have known populations with known exposures resulting in known doses and known effects. That's science. That's not policy. As a buddy of mine used to say, rats don't lie. You got a dead rat, it's dead. And it doesn't matter how you spin it, the rat's dead. And if the rat didn't die, the rat's still alive, and it doesn't matter how you spin that, whether you like the fact that the rat's still alive or not alive, the rat is still alive. So rats don't lie. So in our animal models, A happens or B happens, and if you don't like the data, too bad, that's the reality of it. And that's where we are with this. So we take a look at one of the largest studies ever performed. 7 studies were combined. The U.S. Hanford Nuclear Facility, Oak Ridge, Rocky Flats here in Colorado. I used to teach toxicology, radiation tox and safety at Rocky Flats, by the way. Sellafield in England, and then 2 unspecified sites in England. Those were known as BNFL sites. And then 1 site in Canada. And what they did was they looked at, this was a DOE study. NERO. This is what's known as the NERO study. 95,600 workers. That tells us that we have a large cohort. We have a large enough population that we're minimizing sampling error. We have a statistically good population. 60% of those workers received effective doses above 1 rem. That's an actual unit of radiation. That's an actual unit of dose, not like a picocurie per liter. That's how much radiation went into the human. There were 15,800 deaths out of the 95,000 workers over the study period. Of that, there were 3,900 cancer deaths. What the study showed us was when we look at all that data, that as the radiation rates were going up, cancer rates are going down. Not the other way around. So there is good correlation, but it's negative correlation. This very large study showed us that as the workers were being exposed to more and more and more radiation, their cancer rates were declining below what was expected. Now, when I say expected, what that tells us is the model we're using for our expectation is wrong, because rats don't lie. And if we have fewer people dying from cancer than are supposed to be, it tells us something else is going on. Our model is incorrect. So we need to adjust the model to make sure that the model fits reality. And by the way, this type of a study, this is just one example. Dozens and dozens and dozens and dozens and dozens and dozens and dozens, and they all show the same thing, including for residential radon. So we say, okay, well then, we looked at the dose risk curve, we saw the fish, and we saw that that's a linear relationship. We saw this sigmoid looking thing, and there's a linear relationship stuck in the middle between 2 doses. So what actually is the case for residential radon? Well, what the US EPA said was they took their lowest dose in their study. That was 80 million picocurie per liter years. That was their lowest. 80 million picocurie per liter years. And they put a dot on their graph paper, and I kid you not, they took a ruler, and with a pencil, they drew a line from the lowest dose to 0. And they said, that's our dose risk curve for radon. It is known as the linear, no threshold dose response curve. It is fantasy. It has never been accepted by anybody, including the EPA. Even the EPA says, our model has no basis in fact, but by golly, it's good policy. Okay, now the radon industry would have you believe this, that, oh, no. It's because of the uncertainty, this is the dose risk curve. It's hyperbolic. It's actually much higher because of the uncertainty. And see, we start to get into fear. Uncertainty. Yes, of course there's uncertainty, but we already know what the certainty is and the uncertainty is. So instead, this is what we really see with regard to radon concentrations and human exposures. We see that as the dose increases, we see that the risk cancer risk actually goes down. As residential radon concentrations go up, lung cancer rates go down. Once we start to hit about 100 to 200 picocuries per liter, we are now back to normal background cancer incidence rates. So this is where people who have a little bit of radon in their house, okay, where they have less radon in their house or no radon in their house, their lung cancer rates are going to be background. As the radon concentration starts going up, cancer rates go down. Then as the radon continues to increase, we get back to normal background, and now above maybe 100 to 200 picocuries per liter, now we start to see it going up. So